When you first learn how to solve basic equations, you learn that every operation has an opposite, if you will. For example, to solve x minus 3 equals 5, you want to change both sides to get x by itself. And the operation you use to do that is addition. So if you were to add 3 to both sides, the 3's cancel on the left, leaving x by itself and giving you the answer x equals 8. In the second equation, y plus 4 equals 7, to undo the plus 4, you use subtraction. If you subtract 4 from both sides, they cancel on the left, leaving y by itself and giving you y equals 3. For the equation z divided by 3 equals 6, to undo the division by 3 on the left, you use multiplication. If you multiply both sides by 3, the 3's cancel on the left, giving you z equals 18. And on the bottom equation here, 2w equals 5, to undo the multiplication by 2 on the left-hand side, you use division. The 2's cancel on the left, giving us w equals 5/2. So for each of the 4 operations, addition, subtraction, multiplication, and division, every operation has an opposite, if you will. In the top equation, the opposite of subtraction is addition, the opposite of addition is subtraction, the opposite of division is multiplication, and the opposite of multiplication is division. But how do we undo more complicated expressions? Look at the equation x squared equals 4. What operation do we use to get x by itself here so that we get x is equal to what the answer should be? Or what about other exponents, like x to the third equals 8? Is there an operation that's the opposite of cubing so that we can undo the cube in order to give us the answer to this equation, x equals some number? And this can go on with different exponents as well. And this is why you want to learn about roots and radicals. Just as every operation has its opposite, when you're working with exponents, you also need a way to undo that, if you will, so that when you have an equation, you can find what the answer should be. First, let's remind ourselves what it means to take a number and raise it to the power of a positive integer. If you were to look at x squared, what this means is x times x. X cubed means x times x times x. And x to the fourth is x times x times x times x. It's just repeated multiplication. That's what the exponent is. It's just a notation. It's just a way of writing repeated multiplication very compactly. More generally, x to the nth power is x times x times x times itself n times. For example, 3 to the second power, which you also say is 3 squared, is just 3 times 3, which is 9. And 5 to the third power, which you can also say is 5 cubed, is 5 times 5 times 5, which is 125. So this is how you take a number and raise it to the power of a positive integer. Next, let's look at negative exponents, specifically negative integer exponents. X to the negative 1 power simply means 1 over x. X to the negative 2 power means 1 over x squared. X to the negative 3 power is 1 over x cubed. In general, x to the negative n power means 1 over x to the n. So when you're dealing with negative exponents, what that means is you first flip it over and do the exponentiation. So for example, 2 to the negative 4 power is 1 over 2 to the 4th power, which is 1 over 16. Let's look at one big exception. 0 to any exponent is going to be 0 with one exception. Any number to the 0th power is 1 with one exception. And that is 0 to the 0th power is undefined. What does that mean? Why is 0 to the 0th not defined? The reason is, mathematicians took a technical look at this. And the idea is, okay, well, what number should this be? Any number they came up with led to some mathematical problems. And because of that, there's no way to give this a clear, consistent definition. That's the one thing that's off limits. You can take any complex number to any other complex number power, but you can't do 0 to the 0th power. But the main takeaway is this is how you take a number to the 0th power. So you now know how to take any number and raise it to a positive integer power, a negative integer power, or the 0th power. we're now ready to take the next step and look at different types of exponents. Specifically, we're going to look at fractional exponents. To start off, let's consider 3 to the 1/2 power. What does this mean? That's the first thing I want you to focus on, is understanding what this represents. So this is some number. We don't know what number yet, but we will soon. Now imagine squaring both sides. On the left-hand side, you just multiply the exponents. 1/2 times 2 is 1, so we're left with 3. And this is the reason why I wanted you to square both sides, is we now have this relationship. We have this equation here that uses positive integer exponents. That gives us a way to understand what 3 to the 1/2 power is in terms of stuff that we already know. 3 to the 1/2 power is some number that, when squared, gives you 3. Let's look at a slightly different one. What about 5 to the 1/3 power? Once again, this is going to be some number, and we don't know what yet. But I want you to have an idea of what that number represents. Similar to before, we're going to cube both sides. On the left, you multiply the exponents. 1/3 times 3 is 1, so we're left with just 5. So we've now manipulated this so that we can look at this in terms of exponents we already understand. So 5 to the 1/3 power is some number. That number, when cubed, should be 5. And that should give you an intuition of what this means. So when you look at 5 to the 1/3, you should immediately think to yourself, okay, this is some number. I don't know what it is yet. My calculator does. But when you cube it, you get 5. And this brings us to the idea of radicals. Radicals is just a different way of writing this. That's all it is. It's just notation. Notation is how you write something down. So 3 to the 1/2 power is some number. And the way you write this, or an alternative way to write this, you don't have to write it this way, is this. So this on the right-hand side is a radical. This funky symbol here is called the radical symbol. So all this means is this is some number when squared that gives you 3. Now let's look over the right here. 5 to the 1/3 can also be written using this notation, but a little bit different. We now put a little 3 on top of that funky symbol, the radical symbol. So why didn't we put a 2 here? You could. It's just when there's a little radical with a 2, that's so common, people often leave off the 2. So we're now ready to give the definition of a radical. If you take some number x and raise it to the 1/nth power, radicals are just a different way of writing this. So you can write this using radicals, using the radical symbol as n and the x inside. So really there's nothing more complicated or in-depth to this. The expression on the right is just a different notation, a different way of writing x to the 1/nth power. So x to the 1/3, or the 1/3 power, you could also write it as 3, radical symbol x. X to the 1/5 power would be a 5, radical symbol x. X to the 1/9 power would be a little 9, radical x. However, x to the 1/2, when you're looking at 1/2, when n is 2, you don't write the little number. You just write this. So now what I'd like to do is just take a moment and teach you how to say this out loud. 3 to the 1/2 power, you could write it like this. You won't get in trouble, but because the denominator is 2, people leave it off and they just write it like this. So on the left-hand side, you say that as 3 to the 1/2 power. On the right-hand side, you say that as the square root of 3. What about something like x to the 1/3 power? You can write this using the radical symbol as so. In this case, because the denominator is not 2, you want to put that little number there. And the way you say this out loud is the cube root of x. What about 1/4? You write this using the radical notation as a little 4, radical symbol x, and you say this aloud as the 4th root of x. 1/5, you can also write it like this, and you say that out loud as the 5th root of x. And in general, if you have x to the 1/n power, you can write that as this, and you would say that out loud as the nth root of x. So for example, 7 to the 1/9 power, you could write it like this, and you would say it out loud as the 9th root of 7. So only the first 2 roots have a different way of saying it. When it's 2, you say it as the square root of what's underneath. When the denominator is 3, you say it as the cube root of whatever number's underneath. But for 4 and more, you always say the 4th root, the 5th root, the 6th root, the 7th root, and on and on. And if it's a variable like n, you just say the nth root. Now, as you learn algebra, you'll want to memorize a few things just because they come up a lot with examples. For example, what is the square root of 4? Well, it's a number that when you square it, you get 4, so we know that's 2. By the way, negative 2 squared is also 4. So this raises an important question. Is the square root of 4 2, or is it negative 2? After all, 2 squared is 4, and negative 2 squared is also 4. So it seems like there's two possibilities. Well, the radical notation goes ahead and makes a choice for you. When you take the square root of a positive number, you'll have two different numbers to pick from, a positive one and a negative one. The radical notation says, take the positive number. What about the square root of 9? A number that when you square it, you get 9, well, that would be 3. Well, what about the cube root of 8? Well, it's a number that when you cube it, you get 8, and that turns out to be 2. And by the way, you can check all these here. 2 squared is 4. That's correct. Here you can check this. 3 squared is 9. Check. You can verify this. 2 to the third power is 8. Check. By and large, the more computations you do and the more problems you solve, you're simply just going to use calculators and computers to calculate the roots for you. Let's see a concrete example. Let's compute 3 to the 1/2 power. We now know that you can also write this as the square root of 3. Now this is some number and we don't know its value yet. You could just ask a computer or a calculator, but we'd like to do this manually a few times just so we really have a deeper understanding of what's going on. Now this is some number that when you square it, you get 3. Let's take a guess. Is it 1? Well, if you square 1, you get 1. That is less than 3. If you square 2, you get 4. That is bigger than 3. So whatever the square root of 3 is, we know it has to be bigger than 1 and less than 2. So let's try a few other things. What I want to do here is make a table here of some numbers, some guesses, and over here we'll square it to see if we're getting close to 3, if we're too low or if we're too high. What about 1.5? If you square that, you get 2.25. Too small, we need to get a little bigger. What about 1.6? If you square that, you get 2.56. Closer, but it's still too small. What about 1.7? If you square that, you get 2.89. Still too small, but we're definitely getting closer. What about 1.8? If you square 1.8, you get 3.24. Too big. So we know it has to be between 1.7 and 1.8. So the square root of 3 is bigger than 1.7, but less than 1.8. So we're now going to come over here and get a little closer. We know the first two digits are now 1.7. In fact, I will even write that up here. It's 1.7, but we want to now find what the second digit is. So before, this will be our guess, and this will be the square. If you were to look at 1.70, well, we did that already. That's 2.89. What about 1.71? If you square that, you get 2.9241. What about 1.72? If you square this, you get 2.9584. Still smaller than 3, but we're getting closer. What about 1.73? If you square this, you get 2.9929. Much closer, but we're still not there. I have a hunch this might be too big, but let's see. 1.74, if you square that, you get 3.0276. We're now too big. So we know the next digit is 3. It's going to be 1.73 something. Let me add that 3 up here to the top. Let's find one more digit. So we're going to, once again, have a column of guesses and a column of their squares. And we know the first two digits are 1.73. So if you square 1.73, we did that previously, you have 2.9929. What about 1.731? Get a little bit bigger. Square that, you get 2.99636. Let's go and check the next possibility, 1.732. Square that, you get 2.99982. It's still too small, still less than 3. What about 1.733? If you square that, you get 3.00329. Now too big. That lets us know it has to be between 1.732 and 1.733. So we'll put a 2 there. Now, if you continue this over and over and over, you would find that the next few digits are 0, 5, 0, 8, but this would continue. It would never stop. So how do people do this? So what we're doing now is not the best way to do it. It's a slower way, but there are tricks and techniques to speed this process up. Before the dawn of computers, what people actually did is mathematicians sat down and they worked hard to make tables, like what's the square root of 2, the square root of 3, the square root of 4, 5, and so forth. And they actually wrote these down to a certain number of digits and put them in books. So people would actually have reference books on their desk where if you ever needed to take the 4th root of 9, the 7th root of 2, the nth root of this or that, you would flip through and find the numbers to help you out. Nowadays, we can automate that process and just have our calculators or computers do it. Now, this is not how your calculator or computer is doing it. There's some more advanced math called calculus, and what they use is they use techniques in that to be able to help them calculate roots to any number of decimals. This is what radicals are. If you take some number and raise it to the 1 over nth power, you can rewrite this as this. This is the radical version of writing this down. And you say that as the nth root of a. So the left-hand side, you say that out loud as a to the 1 over nth power. On the right-hand side, you say that out loud as the nth root of a.